So welcome back to the second part of the lecture, where we will talk about Koldoff's prospective spatiotemporal scan statistic. And after talking a bit about the theory, we'll look at an example of applying this to data from Germany. So first, let's look at Koldoff's prospective scan statistics. So this is a paper by Martin Kulldorff, who originally is from Sweden, but now is at Harvard University. And it is an extension of a spatial scan statistic, which they proposed in the 90s. The important part of this is that the method assumes a Poisson, underlying Poisson distribution, so the number of counts in a particular region, and I'm going to really talk spatial here, so I is going to be a region, and T is a time point. It's going to be a Poisson distributed random variable with a QIT, which we'll call the relative risk, and an offset, or well, let's say an expectation of BIT, well, not expectation, an expected count of BIT. Maybe that's the better explanation of what this is. So the expectation of this altogether will be QIT times BIT. That's the important part. So hang on, can we try to annotate this to make it clearer. Draw like this. And we would, so the point is that we will have EYIT. We'll simply be able to QIT times BIT, and we will say this here, this is a parameter, and this here will be known and is specified in advance. So this could, for example, be a population at risk or something which is proportional to the population at risk. Different ways to calculate that expected value. And what is important is, of course, that this QIT, which we will call the relative risk, if QIT is larger than 1, then the expected number of cases of YIT will be larger than BIT. If it's smaller than 1, then it will be smaller than BIT, and then 1, then it will be the expected value will be equal. And the important part, so this is the parameter here of interest, and we're going to specify that it's going to be within if there's no outbreak, so for all regions and all time points, it will be equal to the same value, Q, right? So there's really no difference at all over the regions or the time point, and this will be our null hypothesis, right? So the null hypothesis is saying something like, for all regions, so maybe just going to write that here. So H null will be something like, for all regions and time point, we will have that QIT is equal to Q, same overall parameter. And we will contrast that with an out of control or alternative hypothesis, which says that, well, there are some areas, and areas here we not only mean spatial, but spatial temporal. So we will talk about a space-time window W, which consists of some regions. So that will be the regions will be Z, and a time window. T is the most recent time point, and going back in time. I think in previous notation I could also call that small t naught. But what we really mean is that this will be a window of D, capital D time points, which are the most recent. So this is the most recent, and then going back D minus 1 additional time points in order to have a total of D time points altogether. And the alternative hypothesis is that outside our space-time window, we will have a lower parameter again. You can discuss whether that should really be Q in this case, or if it should be a Q bar, let's say, so a corresponding estimate outside. Of course, if some will be higher, some will be lower. That you can debate what is the best way to do. And let me try to share screen. I want the whiteboard like this, right? So you could say our H1, so our alternative is something that, so we have that QIT is equal to the same overall parameter QW for regions and time point within our particular window. And it will be QIT will be Q bar, which means the complement set of W for IT in W bar, right? So that will be our alternative hypothesis. So these are the regions here, and of course we will assume, just that this makes sense, that QW, so for areas in our outbreak window, we will have that this is, you can debate if you need the equal one, but you will definitely want that bigger or equal to the QW bar. Otherwise, it doesn't make a lot of sense to really look at it if it's lower there. So that's our alternative hypothesis, and that's when we try to look upon. And let's go back to the slide then. Playing around, where is the, should be down here. Yeah, so that's the one. And so what we really try to do is to do a hypothesis. We want to decide which of the two hypotheses actually do we believe in at a given level of significance. And we want to at least find a way to try to distinguish between the two. And what we will do is we will calculate the maximum likelihood estimator, or an estimator of QW and QW bar. And then we will calculate the likelihood ratio between the two hypotheses. So we will see how likely is the alternative, how likely is the null hypothesis, and we'll build the ratio between these two likelihood values, and then we will calculate this likelihood ratio for all W of interest. So lots of W to look at. And then we will only take the one which has the maximum discrepancy between the alternative and the null hypothesis. That will be our most likely cluster. And then we, of course, also want to know something about sort of like, is that the discrepancy is so large that we think this is not by chance, but it's at least something which is so unusual that we rule out the chance by that. And for this, we will calculate a p-value, and we'll get back to that. Okay, so maybe first, as an example, so how could this look? And I will go again to the whiteboard, which we have here. So let's say we have a number of region. Oops, not like this. And not sure why it's not drawing. Draw. Yeah, I need a new share. I want the whiteboard to be shared. And hopefully sharing is paused. Resume. You are sharing screen. Sorry about that. I'm having a bit of problem figuring out what's going on. So this is what we want to share. Your screen sharing, and now I want to switch to the whiteboard again. New share, I will share the whiteboard. Sharing, it doesn't, this is a bit strange. I'm not able to share the whiteboard. So you probably, when you watch this video, you will decide to scroll over all these pages, which is a good thing. Let me clear all of that, clear all my drawings. And continue from here. So I remove that. Just a whiteboard. Apparently, yeah, sort of a bit messy. So this is the thing I want to share. These are the slides. So maybe I'll just do it here and try to annotate in here. I think that's easier. And then I can take it from there. So imagine here we have some spatial areas. I'm going to take this very simple. We will have, let's say, several areas. And what we will then dive, so this would be, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that would be our n here would be the set 1 to 9. And time points, let's forget about that. But let's say that the spatial part, so the Z of our window consists of the regions 1 and 2. And that means we're looking at everything which is the counts of these two regions. And the complement of this would be then 3, 4, 5, 6, 7, 8, 9. Again, also, if you want to take time into account, of course, that's a bit more complicated and so on. And so we define some helping quantity. We'll define the IW or YW simply to be the sum overall counts which are spatially and temporally located in our window. So that would be, for example, the 1, 2 over all the time points, the D time points we're looking at. And let BW be the same, but for these expected counts. And then we have the overall counts, which is simply the Y counting overall region and overall time points. And of course, we can then, so something like Y bar, if you would, is simply defined as Y minus YW. So that would be the counts in all the region over all the time points which are not part of the outbreak window. So that would be, for example, something like this here. So that's the stuff that we can define. And what is interesting now is that, let's say we have these regions like 1, 2, or which are located in our window W. So we are interested in the W estimate of the Q. What's the case count there? And there we can use a technique which is called the method of moments. So I can clear this one here. I can close the window and I should now be able to share the whiteboard. I'm not sure that for some reason, which I don't know why, I'm not able to share the whiteboard, which is a bit irritating. So resume share, new share. Let's go back to our original share, which is the okay. Okay. Not sure where that is. Annotate. So I will take a new share. We'll try again by the whiteboard. Sharing expose, bring your shared device to the front. Okay, maybe I need to bring the okay, I know now why it was. For some reason, when you use the Wacom board, it doesn't put the window in the front. Yeah, sorry about that. Still learning some of the techniques. I hope you can fast forward this when you have to watch it. So what I was trying to do is to get an estimator of this relative risk parameter in our model. And what a simple way to do this estimation is the so-called method of moments estimate. And that means that we simply equate what we observe, which would be for each region yit, with its expectation. And just write method of moment above that, so that we will equal that to the expectation in the area. So this is the estimator for QW, which we try to look at. So it will be QW times BIT, right? That's what we will do in each region. And then this is the equation we get for each. So that means that for all I and t in our space-time window, we will have that yit is equal to qw times bit if we do this method of moments estimator, right? And of course, we can not only say that's the case, but then since the QV is everywhere, we can start to sum a bit. If we, for example, thus look at the entire region, so that's YW, so that means we're going to sum up, sorry, let's take that way and get back. So we're going to sum over all regions IT, which are in W. And what we want to do, of course, is sum this. And then we would equate this when we use the method of moment by the sum ITW of QW times BIT. And then you already see that the QW doesn't depend on this, so we can pull that outside the parentheses. And then we have here BIT summed over all the space-time blocks which are in W. That is simply, as we defined it earlier, this is simply BW, right? And if you put these two together, right, that YW and T is the parameter we are interested in, we would have that an estimator for QW by the method of moment would be YW, so the sum of all counts, divided by the expected value of all counts in the of all regions within the space-time block. Right. So that would be sort of like one method of moment estimator that we have. And we can then go back to our slide to sort of check. All right. So that would be the YW divided by BW estimator that I just showed. And you can do the similar equation. It's very simple, that it's YW overline divided by BW overline for the estimate of the outside the space-time cluster part, right? And if you do this, then you can say, now I'm going to contrast this is a null hypothesis and alternative hypothesis that I just wrote up. And so how will this look? Well, you're going to contrast the two hypotheses, so you will get a likelihood ratio expression. So you need the two likelihoods, which are just sort of like representation of how likely it is to observe the data on a given parameter model. And for that, I'm going to again change to the whiteboard. Hope to bring that whiteboard front page. Get a new page. So starting to learn this. Only one lecture left to learn this, by the way, so it was about time. So we're going to look at here. we're going to say we're looking at this likelihood ratio expression. So it's going to be the likelihood for the alternative model divided by the likelihood under the null model. So let's maybe take I'm going to take like the null model first. So we're going to say we're going to look over all y and t. You can simply write it like I'm just going to write here. Yeah, omega, maybe that would be my expression for that here. I have to write that here somewhere. That omega is this over all regions and Cartesian product with all possible time points, like this. So what we will do is we will take the Poisson probability mass function of each observation here, y t, given that the parameter is the overall q, and that would be sort of our likelihood under the null model, and then you're going to contrast that with what is the likelihood under the alternative, and that would be for those within the cluster. We will have one distribution here, again the Poisson distribution, but with parameter qw, and for those outside, so that means it not in w or equivalently to the w bar, we will have that it's f y I t q w bar, like this, right? And now you can sort of like, these are Poisson likelihoods, so you can start to look up how they will look, and we can skip the parts which are constant to all of it, which don't involve the qw and the q's and so on. So that will be that this will be then proportional to that you will have here the first product. I'm simply going to skip writing the subscript, and you have here the qw to the power of small mistake. It's not simply the q. We need the full stuff. We need here, that would be the bit, that would be the parameter times the qw, and that would be to the power of yit. And then you have for the other, again, this is this product here. I'm simply going to be lazy and not going to write the denominator here. So that would here be the bit times qw, like this. And then I realized that I here forgot the x minus bit qw. Sorry for the mess. And here I would have exp minus bit qw bar, like this, right? And down here we would have that it's simply product. Also, I'm not going to write for what, but it's this one here. So this is overall. And here we would have that it's bitq to the power of yit. And then here you would have exp minus bit times q, right? And what is q? Yeah, well, that's the overall estimate, where q is equal to y overall divided by the b overall, like this. What you will notice is that at least these bits are going to quickly cancel, because you have the bit to the power of yit for all those in the window and outside the window, which is equivalent to that. So that these here at least you can be quick about forgetting about these. And maybe the question is what happens with the remaining B here, and that's when it takes you a lot of fiddling. And what is important is that this likelihood ratio is computed not because we don't know the Q, we will replace them by their estimators, right? So this one, and this one here will be replaced by its estimator. So that will be the for the Q, it will be y over b, and here it will be for the QW, it will be as described on the last slide, also for QW bar, right? And you can, if you do this, the math for all of this here, cancel and take some terms away, which are irrelevant due to proportionality, then you will arrive at this expression here, where you have the little caveat that you say, well, the likelihood ratio, it's really a restricted maximum likelihood estimator that you're using, because you want that. Now I have to take, where is the annotate here, like this, because you really want to sort of like ensure that QW is bigger than QW bar, or at least like this. And I mean, it doesn't matter if they equal, then this will be 1, right? So the likelihood ratio, the smallest it can get is 1 or larger. And of course, larger means that there's a big discrepancy, and there's a cluster of cases. Right. Okay, so that's the stuff you can compute with that, and that gives you a likelihood ratio value. But of course, with a likelihood ratio value, you're not done. As we said here, you take the one overall windows of interest, and now the window of interest, what is that? I mean, it's really, and here we said it's simply any, for example, in the spatial components, any subset of the n, but of course you would usually take those which are geographically connected. And that, of course, greatly reduces the number of subsets of region which you need to test. Okay, so you will try it out. You will try that for several or many of the W, and then you will take the one which has the largest lambda. And then you need to assess, is that largest discrepancy, is that by chance, or is that sort of like, well, can happen, right? And for that, you want to have the distribution of your largest, the most likely cluster, let's call that, of the likelihood ratio of the most likely cluster. And of course, it would be nice if you had an analytic distribution for this one here under the null hypothesis, but you don't. So a standard trick is to do then a Monte Carlo estimation, where you simulate data under the null hypothesis and compute the statistics each time on this null hypothesis, and then you assess how far out or how unusual your actual observed value is under the null hypothesis, right? So since it's all Poisson random variables, if you condition on the total count, so that would be the capital Y is equal to capital C here, let's say, which will be the total count, so it's really observed value, then you can quickly draw values from this distribution under the null hypothesis by simply using a multinomial distribution where these expected values enter, right? So it's simply distributed according to the multinomial, how many counts fall within each space-time block. And once you have that, you get one count. You can compute your lambda as before, like this, and then you will get a series. If you repeat that, and we will repeat that r time, you will get a series of likelihood ratio values. And what you then do is you simply count the rank that your observed value has within this Monte Carlo sample. So you can say that you do it 999 times. You have one extra because of you have an observed value. So there will be a total of 1,000. And now you simply count how many are bigger or equal to the observed value, which means they would be more extreme, and that's exactly where your definition of a p-value is. And then you divide by the total of your sample, which is 1 plus r, because you had the one already observed in the r you sampled. So this is equals to the rank, or it's, you can also simply just say this is the Monte Carlo p-value, and then you can assess this. Then you of course need to to fix some kind of threshold that it's maybe 5% or maybe something smaller. And if your p-value is below that, then you will react to this. Right? So as I said, typically you would take something which is just short of a nice number by 1, because you have this one additional observation. And again, you have to, but we really are not going to talk about this in this course here. You need to think about that you have a multiple testing problem, because when you will repeat the analysis for each time point. But what you have taken into account is that you have a multiple testing problem, because you have several yeah, and have you really that? Yes, at least that you are, because you're only looking at the maximum, you don't need to worry about much about this multiple testing, that you consider several regions, because you're only looking at the maximum. Okay, so maybe just to sort of like complete this, this Koldov scan statistic is quite popular, because it was provided with a at least free to download program called StatScan, but it's not open source. It's closed code, so you don't know what's going on, but it's implementing this algorithm in a very, very efficient way. So this has been highly optimized. There's an R package which simply interfaces to the standalone program. So I'm not sure it works on all platforms, but it works on Windows and Linux. And that can be used and called through R, through the R StatScan package. But there's also a true, what I would call a true open source alternative, where you can really access the code, which is based on efficient data table and RCPP in parts, and this was part of licentiate work by a former PhD student here, which I was partly supervising, Benjamin Alevius. And he, as part of his licentiate work, has written a package scan statistics, which implements several different space-time detection programs, and the scan Poisson PV Poisson function is the one which implementing the prospective stat scan detection algorithm. So maybe without further ado, let's look at how this can be applied to monthly counts of meningococcal diseases in Germany, which is work from a paper which we worked on, trying to model how this meningococcal disease spreads in space and time. And one of the objectives also to be able to detect clusters in time. So that's something which they do at the National Reference Laboratory for Meningococcal Disease. And we will use monthly data, because there are not really that many counts, and there are quite some counties in Germany. So you will really, I think we have about 800 and 600 cases in total for the period of time that we are looking at. So it's not really a large number of cases. So we use month, and many of these districts will have 0 count. We will use here something, how large is the population relative to the total number of counts here for the estimate, as an estimate for the expected number of cases. And you will see here that when we do this for the largest, so there should probably be a star here, because this is the largest region we're looking at. Yes. So you will see here that starting November, May here, we will have we saw a larger cluster in these values. And if you use sort of calculate backwards from the p-value, you will see here we can formulate critical value on the lambda star. And if it's above that, we will likely say we will reject the null hypothesis that there's no outbreak. And here we will say there would be an outbreak. And if you really look closer to the data from entire Germany, you see these are the the region, the maximum region where this is generated, is consisting of 4 regions in the district of North Rhine-Westphalia, or the federal state of North Rhine-Westphalia, which looks like this. So this is the biggest federal state in terms of population, 17 million, and very close here to the Dutch border, which is located, the Netherlands are located here. You have these 4 regions, including the city of Aachen, where you have a spike in cases here in the beginning of end 2004, spring 2005. And that was actually a cluster of cases, and there was a spillover also from the Netherlands of cases here. So this is something where you can see, again, used only spatially connected regions, but this gives you some idea about what you can use this for, that you here have an increase in number of cases in a particular time interval. So it's not just over space alone. This was the early methods when you use that often in cancer epidemiology, when time is not that big of an essence, but here you could also use it with a time window, and that's what we did here, even though I only show in the illustration the spatial component. Just sort of some outlook about things which you would discuss if the course would be longer and there more time. And then we could also talk about whether the Poisson distribution is a good distribution here for these data, because we have a lot of zeros in our data, because it's not that many cases, quite long time interval, and maybe also because if there are cases of meningococcal disease, you might start looking closer for it or more carefully for it, and maybe some cases are either otherwise missed. Doesn't happen that often, probably, but at least, and maybe that's really the point of drawing your attention to this, there is some work to also implement it in this outbreak by Benjamin, and he works with something which is called the zero inflated Poisson distribution, which is the Poisson distribution with an additional extra weight of that you can observe 0 cases. And there's a paper in the Scandinavian Journal of Statistics which talks about that. So maybe this is just to sort of give you an idea. I'm not sure how many of you will ever use that, but please be aware that infectious diseases are not the only discipline where this is used. If you go to the SAT-SCAN homepage, which I linked here, you can really get many examples of where this is used in criminology, maybe also to detect clusters of particular crime events, but it could also be in ecology and other disciplines. So this has been really a famous package or software package used in many disciplines, and you now start to get a bit of idea about this prospective cluster detection that we are again only looking backwards in time. We don't have the opportunity to look forward because the data are not available, and we will have to repeat every time. So one option we always have is also to say we're not going to look, we need more data, we cannot take a decision yet. So that means sort of not to reject the null hypothesis. This doesn't mean we accept the null hypothesis, which you never do. You just say we need more time. We will look next week or next time slot to see what happens. All right, so this should give you an idea maybe that you can also do the multivariate statistic. Of course, it becomes a bit more complicated, and also the Monte Carlo simulation is also something computer intensive. So quickly, if you have a lot of tests to do, you run into computational problems, of course, but that's when sort of like the statistics and the computational part, when they become higher focused, then of course this is also turning interesting from a computer science perspective. Again, these type of cluster detection methods, this is also something which in maybe more modern terms you could say would be part of machine learning, data mining, trying to find the needle in the haystack here, where is a possible detection, and do we know reasons for this. Okay, so with that, I'm gonna stop this lecture number 10, and I look forward to see you in the live session on Tuesday. Goodbye.